All right. Hello, everyone. Happy Tuesday. All right. So today we're going to review for the test, which is planned to be this Thursday. So yes, there's a hurricane. The plan is only to cancel the test if campus is closed. Now, UCF generally is pretty cautionary about things, so that's why I'm waiting to hear from them. If they think that there will be anything which will impede people being able to get to campus and safety and stuff like that, they generally cancel things. So, that is currently the plan. We are planning on having it as long as campus is closed. Campus will be open as if things are safe to get here. Okay? UCF is generally very cautious about these things, so if there is any uncertainty in the safety or anything like that, they generally close things. So, but I'm not going to make that decision because, again, we don't have time to waste. We can't just say, oh, we're going to cancel it, and then there's still everything's fine, and then whatever, and then I'm so we're going to have the test this Thursday unless campus is closed. We are saying this as many times as we can. The current plan is to have the test this Thursday. If campus is closed, we keep saying if, because this is not the plan. If campus is closed, it will get shipped to Tuesday. That is only if campus is closed. I will send out an announcement about that, but the rule right now is that we will have the test on Thursday. Yeah.
So if that happens, will you get an online lecture on Thursday?
No, gosh. If campus is closed, presumably they will extend add a day or something like that. I'm hoping. If campus is closed, no, I'm not going to have you all, in this case, do that, because generally in those cases we'll tack on a day somewhere. Fingers crossed. We'll see. Yeah, if that happens, I would update you all on all the things that would change. It would be a pain, but basically everything would shift if. Big if. It's not here. Anytime I say anything like this, sometimes people miss certain words and oh, he said that the exam's going to be shifted to Tuesday. No. The exam is this Thursday. If campus is closed Thursday, then it'll be Tuesday. I'm just doing everything I can to avoid a situation where campus is not closed, and then someone says, I thought you said it was getting shifted. And then I said, no, I said if bajillion times. So, test this Thursday, still a plan. If anything changes, I will let you know. UCF will let you know, and then subsequently, I will let you know. I will send out an announcement that if anything changes. So, I am at the mercy of the weather and UCF and all that kind of jazz. So, to that end, I think I sadly left all my note cards here, and they are no longer here, which means I no longer have note cards. So, if you do not have a 5x8 note card, I do not have any for you. However, what you can do is just cut a sheet of paper to a 5x8 size. I'll bring it. That's easy enough to do. Make a 5x8 note card out of a sheet of paper. Just, measure it. Obviously, if I see someone with a piece that's way too big, I'll bring some scissors to class, and I'll just cut off the parts that are too big. I'll do it completely arbitrarily what part I cut. So don't. Ideally, I'd have a note card for you, but here we are. All right. So what we're going to do today is I have this PowerPoint slide. Now, I have already posted this with all the work that. So remember, you all are the second class I've taught today. So my studio class, we spent 2 hours and 20 minutes or something like that going through this, and because I gave them time to solve the problems, things like that. We are not going to have that time. So I will still present the problems that I recommend that. I'll present problems and say, hey, these are good problems. In addition, they're just modifications of problems, to be honest. But the full completed PowerPoint is actually already uploaded for you all. So if you all go to the Files tab and you go to Test 1, there is the previous Test 1 review. And then in addition to that is the one where I've worked out everything. It's already there because I've already done it with one of my classes. So there you go. That's there. But this is what we're going to be talking through today. As always, it doesn't do much good to just look at the solutions. It's always good to look at a problem fresh without the solutions. That is just the best way to study because that's what the test is going to look like. Study the way the test will look. Prepare the way that things are going to happen. If you have that's just true of anything in life. So to that end, let's go through this. This PowerPoint slide both has summary slides of like the major concepts you need to know, and then example problems kind of sprinkled in there, here and there. So boom. All right. We have 5 weeks that I've taught you all things. The first week was vectors and units. Make certain you all can work with vectors, break them into components. Make certain your BFFs with right triangles. If you haven't realized the importance of breaking things into components, my goodness, you got 2 days. Like, it's the bread and butter of working with physics and engineering. The world's in components. Oh, thank goodness I actually put my jokes out. All right, how do you get 2 whales in a car? You start in England and you drive west. And you get 2 whales. 2 whales, like the country. How do you get to Wales in a car? 2 whales. 2 whales. Someone else can, 2 whales like the animals, but 2 whales like the location. Wordplay. All right. Good. Okay. So make sure you all know how to work with vectors, both numerically and visually. And make certain you know how to convert units. The basic units that you all need to be comfortable with converting. Here's kind of my list that you all need to be able to do. You need to be able to go from, for example, millimeters. You need to know that that's 1 e to the minus 3 meters. You need to know centimeters is 1 e to the minus 2 meters. You need to know 1 kilometer is 1 e. This is kind of the cheat sheet for. This is all I have memorized. This is the bread and butter base unit, like to be able to go from millimeter to meter, centimeter to meter, kilometer to meter, kilo, centa, milli. Those are the ones that we're going to be using in this class. When you all get to physics 2, I will put those ones on here. They're not going to show up in this class. So I'll kind of put them down here. When you all get to physics 2, you will need to be able to go from nano. And you will need to be able to go from micro. But that is physics 2. Physics 2, you're working with protons and things that are really small. So we use really small. For this class, we'll largely keep it at macro scale. Centa, kilo, milli. That's the ones that you really need to know. Put them on your note card if you think you'll forget it. All right, and then you do need to know the base units. Kilogram is the only weird base unit. Kilogram is the only weird base unit. All the other base units have just like a single letter with no prefix. Kilogram is the only one that's weird. I didn't make the rules. I'm just teaching you all the rules. So here we are. Kilogram is the base unit for mass. If I give you a problem in grams and you're finding force, you need to convert to kilograms. Always be careful. All right, great. Woohoo. All right. You're like, how do I do that? I haven't given you arrows. I'm going to give you all new arrows. I'm going to make them up. It's really easy. Here's vector A. Here's vector B. There's C and D. Which way do I want D to point? I don't want it to go that way. Decisions. There we go. All right. Visually add them. This is a useful skill. To be able to visually add vectors, it kind of lets you check your work. It also visually expresses the math that you're doing. Tip to tail. Tip to tail. It is ill-advised to try to do this in your head. That's going to hurt your brain. It hurts my brain. So the key to adding vectors is you draw one of the vectors. So we draw A. It doesn't matter the order you go in. Addition, 2 plus 3 is the same as 3 plus 2. So you draw A. and then we draw B, and then we draw C, and then we draw D, and our final vector, A plus B plus C, is just beginning to the end. It's really nice. Tip to tail method is what it's called, because you put the tips and the tails together. And the order doesn't matter. You can test that for yourself. You could do D plus C plus D plus A, and it gets you the exact same result. Addition, the order doesn't matter. And what you are secretly doing here is you are secretly adding the X components together, and you're secretly adding the Y components together. Because if it goes to the left and the other one goes to the right, they kind of cancel each other out a little bit. This is actually secretly doing that behind the scenes. So it lets you check your work. Okay, so great. Fairly straightforward, important skill. Lets you easily check things. Now, what I didn't do a great job, I should have given you all more problems like this. There was a few sprinkled in the problem set, but I didn't teach you all how to necessarily subtract vectors. So quickly, we'll just do the exact same problem. I actually have to copy and paste my vectors. So I'm going to steal these vectors right here. There you go. And this one is A minus B plus C plus D. And all I need to tell you all is that subtracting is the same as adding a negative. Subtracting is the same as adding a negative. And what does a negative vector mean? A negative vector is very simple. A negative vector is the exact same vector, but flipped exactly backwards. That's negative B. A negative vector is the exact same vector, but everything is flipped. Instead of being up, it's down. Instead of being to the right, it's to the left. The X component turns to negative. The Y component turns to negative. It flips it exactly 180 degrees. So bam, you just add A plus negative B plus C plus D, and ta-da, now you know how to add. Now you know how to subtract vectors visually. And that blue is a little hard to see, so I'll use purple. But it's handy. You will subtract vectors in your life. But I feel like I didn't do a fantastic job of giving examples of this, so here's an example. But yeah, exact same process, y'all. You draw A. The more accurate you draw these, the better. But at the same time, if I gave you a problem like this, it's not going to be crazy. I'm not going to be like super nitpicky. And ta-da, there's my final result. A plus negative B plus C plus D. There you go. It's nice. Yeah. You had to do mathematically for a problem like for the angle? Yeah, like we have to yeah, so the question was, if you had to do this mathematically, could you just add 180 to it? The challenge there is you want to make a right triangle. So you don't generally want to work with an angle bigger than 90 degrees. So in that case, if you had to do this mathematically, honestly what I recommend doing is, if you're cool with finding the components in the first case, just put a negative sign in front of the X and the Y component. It's fairly straightforward. Yeah. All right, so fairly straightforward, but an important skill nonetheless. All right. 1D kinematics. Position, displacement, velocity, acceleration. Make sure you know what these words mean, and then make sure you know that they're different from each other. I am not going to give you a question that says, what does the word position mean? What does the word velocity mean? But you can't solve problems if you don't know what the words mean. If you don't know the difference between acceleration and velocity, you're going to run into problems. Because the first step in any problem after drawing a picture is writing the givens. So you need to know what the heck velocity is to be able to identify that. You need to know if you're not moving, velocity is 0. You need to know that if you're in the air, the acceleration is negative 9.8, assuming there's no rockets or anything crazy attached to it. You also need to know that the relationship between these is derivatives. So to go from position to velocity, take the derivative. To go from velocity to acceleration, take the derivative. You want to go backwards? Integrate. So there's a few problems that we did with that. So to go from position to velocity, you take the derivative with respect to time. To go from velocity to acceleration, you take the derivative with respect to time. And to go backwards, you integrate. So we'll do a problem with it. And then the kinematics equations. Hopefully you have realized at this point that when you're solving a problem, it's not about looking at a problem and saying which kinematic equation solves it for me. I hope at this point you realize it's write down the givens, write down what you're solving for, then just pick the right tool then just find the one that has what you need and has what you have. I hope that that's kind of settled at this point. If not, that is a very important skill, is realizing it's not about the right equation, in air quotes. It's not about, hey, look at a problem and immediately choose the right kinematics problem. It's about, can you identify the givens and the missing based on all that? All right, we'll avoid this nonsense. All right, so, and the only way to get good at that process is doing the problems, but yeah, these are just different size Allen wrenches. You got to figure out what size you need for the job. It's not about just looking at it. I don't just look at a problem and say that's the equation to use. I write down the givens, I write down the missing. That's just how you do this. It's the process. All right. Yeah, there you go. Not too much more to say there. Yeah.
Could there be more than one equation you can use?
There is definitely more than one equation you can often use. Yes, when solving problems, it is very common. So when we get to like projectile motion, you all very likely use this one to find time a few times. But alternatively, there is situations where the same problem, you could have find a velocity, and then you use this one, vt equals that, to find time. There is very often, when it comes to kinematics problems, more than one way to solve a problem. Generally, at least 2, 3, like, if the logic is good, you're good.
For knowing the integration
Mm-hmm.
is the DET in between, that's the displacement?
That's the derivative. So to go from position to velocity, take the derivative with respect to time.
So displacement isn't like a part of that?
No. To position to velocity will be the derivative. It'll be the derivative of the position equation. And you all can actually see that now. If you all look at this equation for position and you take the derivative of it. If you all take the derivative of this equation, you get that equation. If you take the derivative of that, it's not very exciting. You just get A equals A. So yeah, this is actually how these all kind of came about. We started with A equals A, and then you took the integral, and it gives you VF equals V naught plus AT. And then if you take the integral, it gets you this one. Ta-da! That's where these equations came from. They're all connected in that same way. So they started from, acceleration is a constant, take the integral, and to get all the others. This one is average velocity. This one, you had to do some algebraic tricks. So, yeah.
Are these formulas on the slide?
They are. So if you all want to know exactly which formulas are on the test, go to the Files tab, go to Formula Sheet. Boom. This is the exact copy and pasted. It's on your test. These formulas are the ones that are on your test. For this test, all accurate. I will say for the next test, I'm not going to do stuff with these ones here. I'll update this for test 2, but for test 1, this is literally copy and pasted on there. When we get to test 2, same thing. I'll update this, like a few of the equations. I'll get rid of like 3 of these and change it for 2, because I'm not going to teach you all harmonic oscillators, but I am going to teach you center of mass and universal gravity and whatever. That's test 2 things. This is literally copy and pasted on your test. So if there's anything you're like, man, he doesn't have this, put it on your note card. And this will be on on your all's test, there will be a Scantron. At the bottom of the Scantron will be the formula. So it's nice and right there. There you go. It's a good question. All right. Moving onwards. All right. I tossed an apple straight up with a velocity of 5 meters per second. What is this acceleration on the way up? You got 10 seconds. Yeah, again, and these PowerPoints are, they're online. So if you're like, man, he's going, Just know that's why I also put them online. It can let me go through slides quicker. This is either you know it or you don't. If you're in the air, A is negative 9.8. If you are in the air, A is negative 9.8, assuming there's no rockets or things that are pushing you up and down. When I toss this straight up, gravity is the only thing that affects it on the way up. So if we kind of drew a picture of this, here's the ball in the beginning. It has some initial velocity equal to 5 meters per second. Then it's at the highest point. Then it's on the way down. So the velocity changes. But the acceleration is always negative 9.8 if gravity is the only thing affecting it. And that is the case in this problem. A is negative 9.8 here. A is negative 9.8 here. A is negative 9.8 here. That is very important to remember, and really that's testing. Do you remember the differences between acceleration and velocity? Gravity pulls things down, y'all. Always. I don't care where that thing is in the air. Gravity's pulling it down. And it's causing its velocity to change downwards. That's why it doesn't fly off into space forever, and that's why it comes back down. So, all right. 2D kinematics, all bold, all caps, because, man, this is really the only difference. You have to split things into X and Y. You have to split things into X and Y. X and Y are independent of each other. Never put the acceleration of negative 9.8 with X variables. Don't do it. They're always separated. Time is the only variable that you get to carry across them. Which is why in every single one of these problems, you basically have to find time. And then, there's a few pieces here. In the X direction, if you're going through the air, if it's a projectile motion problem, i.e. something's flying through the air, the acceleration in the X direction is 0, therefore the velocity in the X direction is constant, always same number. In the Y direction, AY is negative 9.8. Remember that direction matters. If you don't put A as negative 9.8, if you put it as positive 9.8, and you're saying gravity is causing it to get faster upwards, that's not the way the world works. So direction matters. These equations depend upon positives and negatives. Positive is to the right, negative is to the left. Positive is up, negative is down. Very, very, very important. If you put the wrong sign, you get the wrong answer. That's just how it's going to go. All right. But once you do enough of these, I know 2D kinematics is like a classic roadblock for many people. Once you do a few of these, they all look the same at some point. Once you get the process, once you understand what you're doing, and this is where I'm going to warn you all, I forgot to mention this, there is a range equation and there is a height equation. Those equations are a little dangerous to use for the one reason that they're kind of a shortcut. And they only work for problems. Okay, well, the height equation I think actually works for any of them. The range equation only works if you start and stop at the same height. If I shoot something off a cliff and if it starts at some height and ends at a different height, the range equation doesn't work. It can be dangerous to use, I call them shortcut equations for that reason. The kinematics equations will always work for you. As long as you put stuff in right, they work for any situation. The range equation only works for a very specific problem. The height one I think does work for pretty much any problem. But you might have found those. I've seen many people that have. You can use them, but they don't help you learn the skills that you actually need to solve a more like the breadth of problems I could ask you. Anyway, the point of the problems I give you all is not to get the right answer. It's can you think through the problem correctly? That is ultimately what I'm testing you all in this test. The right answer, the only reason the right answer is on that paper is you can only get that if you get the right process. It's literally just a way for me to check if your process is right. There is always a random chance that you could get to the right. It's very hard to get to the right answer and the wrong way. The analogy I give for this it's very hard to get to someone's house if you don't follow the right directions. If you take the wrong direction somewhere, you make a left instead of a right, yeah, you're screwed. Like, unless you make two mistakes or you realize your mistake and you correct it. That is just how these things work. It's deterministic, is what we call that. All right, so here's a problem. There's the answer. The answer is a little funny because it just barely doesn't hit the ground. All right, so I throw an object with a velocity of 5 meters per second at an angle of 10 degrees above the horizontal, above the positive x-axis. If this object starts at 1.3 meters, which is roughly the height of my hand, I had a meter stick nearby, so it's roughly correct. We have to throw it and the wall is 3 meters away. What will be its height when it hits the wall? Draw a picture. Think through this problem. What's given? Think about this problem. See if you all can do steps 0, 1, and 2. Writing down your givens, writing down what you're solving for, drawing a picture of this problem. You can do those 3 steps. Step 3 is easy. Just find equations that let you get what you need. Steps 1 and 2, in my opinion, are the hard parts of a problem. So there's the floor, there's the ball. It gets tossed with an velocity of 5 meters per second with an angle of 10 degrees. There's a wall. That wall is 3 meters away. Picture helps. It helps you match the variables. That's the reason the picture is useful. It helps you visualize the problem. And if you can visualize the problem, then you can generally have a better sense of, hey, what do I have position information? Do I have velocity information? Pictures are nice. So here I've given you the velocity of 5 meters per second. Before I even write any other givens, immediately, you can do this in a little bit, you can do it now. I'm going to do it now just to stress this point. That is neither the x nor the y component. It's the total. So I'm going to immediately say, I got to break this into x and y because that's how you always have to break things into x and y. Do it sooner than later. This thing's not in the x or the y. It's not pointed straight up. It's not pointed straight to the right. It is at an angle. You need to be able to draw triangles, specifically right triangles. So there's a triangle. And so I'm going to find how to the right is that arrow. How up is that arrow? That is what the y and the x component are. And I will label those. The initial x, the initial y. We know that this angle is 10 degrees. So Vx initial. And it's very important. Your notation matters. Because if you aren't clear in your notation, it's going to be harder for you to understand what the heck you're doing. So based on our triangle here, my x is my adjacent side. How do I find the adjacent side? I do the hypotenuse times cosine of theta. How do I find my opposite side? I do sine times the hypotenuse. As I've said many, many times, just because it's common for x to be the cosine, it is not always the cosine. Always go through SOHCAHTOA. You're like, that's extra brain power. Yeah, but it'll bite you on the butt if you don't do that. One day it will bite you on the butt if it hasn't already. I've already given you all problems where the x component is sine, and I've given you problems where the y component is cosine. So just do not fall into the trap of x always being cosine. It's a big trap that a lot of people fall into. All right, 4.92. Yay, and that one's going to be something else. Make certain your calculator is in degrees mode. It's always good as you're doing this to see if your stuff makes sense. In this case, it's mostly pointed in the x direction. 10 degrees ain't much. It's mostly to the right. So great. What else do we know? We always know that when it's in the air, a is negative 9.8 meters per second squared. We know the x acceleration is 0. A classic trap that also people fall into is people say it hits the wall and it stops. And so people say that this is not correct. What I'm about to write is not correct. I'm going to put a giant X through it. People think that it is very common that people say this. This is not true. The final velocity in the X is not 0. The reason being, yes, it will hit the wall and stop. But this is like me asking you a problem. Hey, I punched someone in the face. How fast is my fist going when it hits their face? And you say 0 meters per second. Then I'm not hitting him no. You can see why that's not, doesn't make sense. No one's going to say I hit someone in the face with 0 meters per second. Same thing in this problem. We're not going to say it hits the wall with 0 meters per second. How did it get to the wall if it's not moving? So, we don't know the final velocity in the x. Actually, we do know the final velocity in the x direction. It's the same as the initial velocity in the x direction. Remember, x is the same always. There's no acceleration in the x direction, so it doesn't get faster, it doesn't get slower. The x direction, there you go. All right. Cool, that's honest. Sure, there's actually one more thing. We're going to put it is generally, we say the ground is 0 height. You can define things wherever you want, but we're going to say that the ground is 0. We're going to say we start at 0. Look at all these things. We generally say where we start is 0 for x. We generally call the ground 0. You could do whatever you want, though. You could say that the wall is 0 and I start at -3. You could say I start at 0 height and then we're finding the y-fi, whatever. It doesn't matter. It's all relative. It's all relative. The first question I asked you all in this class is, where is Demo Duck located? And I told you all, you get to decide. All right, step 2. What are we solving for? We are solving for y final. What height is it at that point? That's generally relative to the ground. So we're solving for y final relative to the ground. Now, remember, in every single one of these problems, almost every single one of these, there's a variable. I didn't say to find it, but you probably should. Time. Almost a guarantee that you're going to need time to do this. Almost always a guarantee in these problems you're going to need to find time. Just get used to it if you haven't already. So great. Hey, find a kinematics equation. Given all this, look at this giant list of things. Check out your kinematics equation. Oh, and you have to make a decision. What limits the time? Is it hitting the floor or hitting the wall? So which one, x or y? X is going to limit our time in this problem. You have to make that decision. What decides when my thing stops? In this case, it's when it travels 3 meters. That's when it decides when it stops. So, spend a few seconds, see if y'all can find an equation that'll let you find time. Then see if you can use that to find YF. This is the part, basically, given all this, can you come up with a plan how to proceed? Given all this information we've collected, great. Now I can figure out a plan. Now I can choose equations. Fun fact, it's going to be the same equation, just in x and y. We're going to use x of t equals x initial plus v initial xt plus 1/2 axt squared. The acceleration in the x direction, who cares? 0 goes away. See you later. We want time. We have everything else. We have the final exposition. We have the initial exposition. We have that. Yay, we're going to get time. And then what are we going to do with that? We're going to use the exact same equation, but with y's. Why are we going to use this equation? How did I choose these equations? I didn't just put this equation lets me I want to find the final y. Just to clarify this, these are the same thing. And we just go through our checklist. I got this, I got this, I got this. How do you choose the equation is just based on what you have and what you need. So it's not that I pulled it out of thin air, it's that it's the one that has what I need and has what I have. Yeah, and at this point, just plug in numbers. I'll leave that for you all. This is the physics. Steps 1, 2, 3 is the physics. Step 4 is just plugging things in, which is an important skill, but one that you all have been practicing for the last many, many years of your life, and so I'm not going to. We'll move on to more physics things. That shouldn't be a new skill. Step 4 is the easiest step, if you set it all up correctly. Yep, and the answer is there, so y'all can check your work eventually. Yeah. Yeah, if you get like 0.006 or something, you're good. If you're in that ballpark, plus or minus a few millimeters, you're good. That's fine. Yeah, if you're within a few millimeters, you're good. Yep. Generally, I say 1 to 2% in this problem, because we're working with the numbers so tiny, any slight deviation makes it look like a big deviation. Yeah, if you get a number that's around 10 centimeters, you're good. 13 centimeters, 7 centimeters, not 7. Yeah, 7. 7 or 7 millimeters? No, this is not, sorry, that's not 10 centimeters. If you get, that's 1 millimeter, that's
10 millimeters.
10 millimeters, 1 centimeter. If you get the answer around 10 millimeters, you're in the ballpark. If you get 7 millimeters, that's pretty darn close. 3 millimeters is about, if you can't see the gap between my fingers, it exists. It's very tiny.
If you do like 2, you're off by like 5 millimeters.
Yeah, that's where you just have to think about it's millimeters, 5 millimeters. And if you actually thought about this as a real problem, that's pretty darn close. Yeah. 5 millimeters is a very tiny difference. I'm not going to give a problem where rounding will result in that much percent error. Yeah. Yeah. What was the thing? VFY would be final velocity in the y direction. You don't need it for this problem, but you can find it if you wanted to. You don't actually need it to solve this, but you could find it. If you find the time, you could do VFY equals V initial y plus AT. And yeah. All right. So there you go. Projectile motion problem. Classic, right? All right. Here's another two-dimensional problem. But in this case, so I'm giving you a velocity, and it is in vector notation. There is I hats and j hats. And my question to you all is, what is the magnitude of the car's velocity at 2 seconds? The answer is not 14. You will get 14 if you do the wrong thing. You'll find out. I'll tell you all what that wrong thing is in a little bit. The answer is 10. See if you all can figure out how to get there. The key here is, do you recognize what vector notation means? What that I hat means, what that j hat means. So this is kind of a notation problem. And then, part B is, what is the position vector? So how do I go from velocity to position? So, we are going to plug in 2 seconds in here. We're going to plug in 2 seconds into this equation. Make certain you don't just forget that those I-hats exist. Don't forget that the J-hats exist. If you forget they exist, you get the wrong answer. It is subtle, but very important. So you get 6 I-hat plus, you cannot, what does I-hat mean? What does J-hat mean? I-hat is in the X direction. J-hat is in the Y direction. You cannot add X's and Y's as is. You can't just write. So what this is showing is I have a vector to the right that is 6 meters per second, and I have a vector up that's 8 meters per second. These two things are the same. And so if you want to get the magnitude, the total, it is the magnitude, i.e., the hypotenuse. So if you want the magnitude, you got to do the square root of Vx squared plus Vy squared. 6 squared plus 8 squared. It's very nice. It's one of those 3, 4, 5 triangles. Which is very convenient. I didn't plan that when I made up this problem this morning. But it was nice it worked out that way. It's subtle, but basically this problem is saying, do you realize that X and Y are independent? And do you realize that this problem has an X component and a Y component? I don't know what's this class, 3rd, 5th. A huge chunk of a significant portion of this class is teaching you all how to speak math. Like, that is so much of this class, is being able to speak math. Math is a language. Can you speak that language? Can you interpret what the equation means? Given variables and all that kind of stuff, given I-hats and J-hats, I am teaching you all the language. It's the language of logic. All right. Position vector. I'll give you all a few moments. How do you go from velocity to position? That is the question. See if y'all can figure it out. I will reveal in a few seconds. How do you go from velocity to position? Velocity is the derivative of position with respect to time. So, position is the integral of velocity with respect to time. Just seeing, do you understand that relationship? Now, same thing. I's and J's are separate. They stay separated. Do not put them together. So we integrate 3t I hat plus 2t squared j hat, all with respect to t. And we get that r of t equals 3t squared over 2 I hat plus 2t cubed over 3 j hat. So if you want to find the position at 2 seconds, you just plug in the 2. So you get 3 squared divided by 2 I hat plus 2 times 2 cubed divided by 3 j hat, which comes out to 4, 12, 6 I hat, 8 times 2, 6, and 16 divided by 3, whatever that is. It's 16 divided by 3 as far as I care. That's a number. 5.33333. Anyway, what's the magnitude of displacement? Same thing. If you want the magnitude, square root of rx squared, let's actually just x squared plus y squared equals square root of 6 squared plus 16 over 3 squared. I have no idea what that is. 8.03? Sure, why not? It's bigger than either of the numbers. That's a good sign. The hypotenuse should always be bigger than either of the numbers. That's one way you can check your answer. 16 point, that's like 5, that's like 6. This is bigger than both of those. That's a good sign. All right, there you go. I made a little bit of a shortcut. I did make a little mistake here. It's a very subtle mistake, but I actually made this problem purposefully easy for you all. This was an indefinite integral. So it says, what is the position vector at 2 seconds? I did forget something, and so I am going to add that here because it is important. Boundary conditions matter, y'all. So when you all do this integral, it's a little bit, there is a constant. So R of t equals 3t squared over 2 plus c I hat. Both x and y get their own constant. X and y get their own constant. Whenever you all do an integral, there's a constant. You can't forget about that. I did. That was bad on me. Now, I gave you all boundary conditions. I said the car starts at 0, 0. So if you plug t equals 0, you find that c equals 0 and life as well. But I'll let you all look into that. If I was real mean, I would have put the car starts at like 5, 3. And then you'd have to find what c is, and that would change your answer. And it matters. Like, it is something you all got to keep in mind that boundary conditions matter. Case in point, when you all look at the kinematics equations, so kind of just quickly going back to those, if you all look at these equations, if I take the integral of v naught at, that gives me v naught t plus 1/2 at squared. That constant is the initial position. That's where that x naught comes from. If you all integrate this equation, it is plus c. What is c? It's my initial position. That matters. Like, you have to plug that into equations. So that constant is important. And, case in point, same thing here. If I integrate this acceleration, that just gives me at plus c. C is the initial velocity. Look at that. See, it's all connecting, right? Maybe? I don't know. Hopefully. All right, great. Tricks for projectile motion. Remember that the total time equals the time to the top divided by 2 if you're landing at the same height. V initial y equals negative V final y only if you're landing at the same height. This only works if you're landing at the same height you start from. And then the rest of this is true for any projectile motion problem. Vx is constant, break things into x and y. The velocity in the y direction at the top is 0. Just random things that hopefully should be like, yes, I've seen this a million times. Awesome. Great, that's kinematics. Forces. All right, circular motion, remember these are the equations. There was a typo, but it's gone now, which is good. All right, quick test of you all. If I have an object going in a circle like this, draw the directions of VT, draw the direction of AC. So see if y'all can do it. What is the direction of VT at that spot? What is the direction of AC at that spot? It is something going in a counterclockwise circle, and it is located on the left side of it. What is the direction of VT? What is the direction of AC? Your arrows better be straight lines. There is no such thing as a vector that's curved. All vectors are straight lines. If you ever draw a vector that's curved, it's automatically wrong. I don't care what vector it is. That's always true. Any vector is a straight line. There is no such thing as a vector that's curved. Because what the heck, if I have a vector that's curved, what direction does this point? Like that? It points curved, like, you can't describe the direction.
What if you can't draw a straight line?
Practice. Use your note card. Your note card has a nice straight lines on the side of it to draw straight arrows. Or a pencil. Literally, you got lots of straight. Use your calculator. Like, so many things are blocky. It's a good question. It's a little silly, but all right. Centripetal acceleration, really easy. Centripetal, center acceleration. Really straightforward. It's towards the center. Always. All right, tangential velocity. The key to this one, you draw a little line that lines up with your circle, and then you make it longer. And you just got to decide which way it goes. Does it point down or up? Well, it's going counterclockwise. So it points down. This is the direction it's moving at that time. At that time, it is moving directly down. If I let go, whatever it was, stopped turning, that's the way it would go. If this is something on a string and you let go of it, that's the way it's going to go. If you're in a car and you let go of your steering wheel, that's the direction you're going to go. So on and so forth. All right. Newton's laws, make certain you know them. I do not need you to have these memorized, but you better know the consequences of them. Newton's first law, things keep doing what they're doing. Second law, F equals ma. Third law, for every force there's an equal and opposite. Very important that you all know the consequence of these. I am not going to ask a question that says, which of Newton's laws says for every force there's an equal and opposite? No. I will ask a question. I could ask a question. Hey, a truck and a fly hit each other. How do the forces compare? I could ask a question. Hey, you fire a gun in space. What happens to the bullet's velocity over time after it leaves the gun? I can ask those clicker questions I gave you all. Now, one of the problems I do want to kind of practice is the second one, which is a ratio problem. If I double the force and triple the mass, what happens to the acceleration? So that's in the next slide. I have two objects. Object A is 7 times the mass as object B, and I push it with 3 times the force as object B. How do the accelerations compare? And the first key here is write down your ratios that are given. How does mass A compare to mass B? How does force A compare to force B? And then at that point, you can play with the equation. I'll show you all how to do that. Or make up numbers. You can totally make up numbers in these problems as long as they follow these relationships. Make up that object B's mass is 1 kilogram. Make up that object B's force is 1 Newton. You can totally do that. So there's our first ratio. Mass A equals 7 mass B. The next one is FA equals 3 times FB. And we are trying to figure out how AA compares to AB. It's a ratio. Is the acceleration that object A experiences 3 times it, half of it, 5/3 it? That's the question. How do they compare? So how do we do this? You can make up numbers. Totally just make up numbers and, use F equals MA and you can do that. But I'm going to show you all how to do it in a more general sense. I think this way is a little bit easier, but pick your poison. First step, you write the equation that relates them. Second step, what variable do we care about? A. So we rearrange this equation for A. A equals F over M. As F goes up, A goes up. As M goes up, A goes down. It lets us see how things change based on how variables change. And then what I'm going to write it out a bit more than I may need to, but it helps. So we'll write out both of them. AA equals FA over MA. AB equals FB over MB. Just kind of writing each in terms of their own variables. And then you just take these and you chuck them in the equation. Take this relationship and put it here. Nope, not there. Put it down there. Take this relationship, put it right there, and magical things will happen. So let's just do that. So AA equals 3FB. To make these a little bit easier to follow. 3FB divided by 7MB. What's the point of doing that? Pull the numbers to the front. 3/7 FB over MB. This is this. They're the same thing. So you get a ratio. Ta-da! So the final result is that AA equals 3/7 AB. Ta-da! Nice and straightforward, but it's nice. It's a nice kind of recipe for doing any problem like this. Hey, here's two objects. They experience different things. How does this final result compare between them? This is how you can do these problems. Fairly straightforward. We're going to see this a lot because it's a really useful skill to say, hey, I have some situation. I double something. What's going to happen to something else? I half something. What's going to happen to something else? You know, an easy example of this. I have an object. I double its density. What's going to happen to its mass? It may seem silly, maybe like, what's the point? But that's a useful skill that given some situation for you to be able to predict. And I've said this a bunch of times. Hey, if we built it twice as big, how much money is it going to cost? Or if they build it twice as big, how much more force can it withstand? If I double the diameter of this rod, how much more tensile strength can it withstand before snapping? Stuff like that is very useful to be able to kind of do on the fly. All right. Newton's laws, basically, you got to know your forces, Fg, Ff, tension, gravity, normal force, applied force. And all of Newton's laws boil down to sum of Fx equals max, sum of Fay equals may.
Are you going to ask us questions on spring force and drag force?
Spring force is no, there's not really anything about spring force and drag force, definitely not. Now, I say no drag force. There will be a force, like force due to air resistance, but you won't be calculating it using that fancy equation. So yes, there might be problems with air resistance, but it would be, hey, given all these things, find the force due to air resistance using a free body diagram. You will not use the drag equation. Like it was at the end of my PowerPoint, I said, hey, here it is, and goodbye, it's gone. But yeah, this is the bread and butter, y'all. Can you do this? Can you do Fx equals max? Can you do Fy, sum of Fy equals may? And then do you recognize that if something is not speeding up or slowing down, A is 0? That's come up a bunch. You know, we had things hanging from ceilings or not sliding or stuff like that. Okay, and then before I jump to the last problem, okay, I guess there's two problems I'm going to do with y'all. I'm going to delete this problem because it's a little confusing. It's not worth the time. So there's two last things I'm going to do with y'all. Before I jump to, there's a couple problems. They say couple. Yeah, it's just a couple problems. One of them's across 3 slides. So let me jump into this and then we'll jump into the problems. Inclined planes and circular motion. So remember inclined planes, y'all. You got something on a hill. I have a box on it. You got a normal force pointed up. If there's friction, it points opposite the direction of motion. Gravity points down. And you have to split gravity into that X and Y component. Remember, y'all, these inclined plane problems are basically something that's flat. So you got FGY, and then I like to call this FGX because we are defining our X and Y in this kind of tilt your head situation. So these equations over here are kind of the shortcut equations for this. But it is beneficial if you know where they came from. If you just kind of use them as is, they'll work. But one of the key pieces for this is realizing that angle there, that angle of the incline is the exact same angle as right here. And we talked about that, and that's one of those that it is very useful for y'all to be able to do that. To be able to take an angle from one part of the picture and realize it's the same angle somewhere else in the picture. That comes up so much. The angle I give you all is not always the angle that you need. You sometimes have to do some geometry. And there's a few ways to kind of figure that out. So that's that. And then down here, centripetal force is remembering that MAC. So MA equals sum of forces. If we want to just look at something going in a circle, MAC, M times the acceleration towards the center, equals the sum of forces towards the center. When you're going in a circle, this is a math tool. There's a few problems to do with this with the roller coaster. We're going to do one problem kind of conceptually on this. Remember that positive is towards inside. Positive is towards the center. Negative is away from center. We define positive and negative as towards center and away from center because up and down change depending on where you are in the circle. So we redefine what positive and negative is for this. All right. So last two problems we're going to talk through. The last one we are not going to have the time to solve. It's actually your all's recitation problem this week. Woo! But it's good. It's a really good one. If you all can do this problem, you can both do inclined planes, and it's a pulley problem and an inclined plane problem. Yeah, it's good. All right. It's really good if you all can do it. I highly encourage it. All right. So a cart goes around the roller coaster. Whee! Look at it go. My question to you is draw the forces acting on it at the top, bottom, left, and right side. Let's call that point A, B, C, and D. Point A is at the top, point B is at the bottom. Point C is on the side, and point D is on the other side. Draw the forces acting on it at those places. Every single spot should have 2 arrows. And it would be better if point B was flat. Let's just assume the spot here was, I drew it better. Let's, perfect circle. There we go. It's gone. Again. There we go. All right, so the key to this is you just go through your laundry list of forces. Is there gravity? Yep, gravity points down. Is there tension force? No, no strings are attached to anything. Is there a friction force? Okay, I should have said there's no friction here. If you want, you can put friction. That's up to you. It won't affect the next one. We're going to assume no friction. I should have specified that. Draw the forces, assume no friction. Great. Now we're good. All right, no friction because it said so. Is there a normal force? Yes. And this normal force always points away from the surface. Normal force always points away from the surface. So at the top, Fn and Fg both point down. At the bottom, Fg is still downwards, but now Fn points upwards. And you might notice I sometimes use F capital N and sometimes I use F lowercase n. Pick your poison. I don't really know why I switch. It'd probably be good if I used consistency, but all right. Fg points down here. Fn points towards the center. Fn at point D points towards the center. Fg points down. So that part's great. Very exciting. Now my question to you all is which forces combine to give you the centripetal force? So at point A, MAC equals what? At point B, MAC equals what? At point C, at point D. Centripetal force equals the sum of forces towards and away from the center. Centripetal force is it's a useful tool. That's what centripetal force is useful for. If something goes in a circle, it lets you figure out things that you otherwise couldn't figure out easily. If we didn't have centripetal force, this would be terrible. like X and Y components, and they're changing as it's going around a circle, and that it's gross. All right, so we look at point A. Fn, does that point towards the center? Yep. Positive or negative? Towards the center or away from it? Positive. It is towards the center. Plus Fg, towards or away? Towards. So great. There you go. At the bottom, Fn, towards or away? Towards. So it's positive. Fg, towards or away? So it's negative. Towards the center is positive. Away from the center is negative. Part C. Fn, towards or away? Towards. Fg, towards or away? Neither. Fg does not point at, no part of Fg points, if you all had to describe Fg, does it point towards or away? Neither. It's not pointing towards or away. There is no part of Fg that points towards or away the center. It is exactly perpendicular to it. So when you're calculating centripetal acceleration, who cares about Fg at part C? At part D, the same exact thing is true. Gravity. There is no component of gravity that points towards or away from the center. Fg in my picture points exactly perpendicular to it. There is no component that points towards or away from the center. So that's a good thing to think about, think through, logic through. If we were at some point like in between, then there is a part of Fg that points towards the center. And we did a problem like that. That's a good one to look at. There was a problem where I gave you like one in between it and you had to use an angle and do some things. So, anyway. All right. There's that last problem I'm going to show you all. And we're just going to do the free body diagram part of this because that's the part we have the time for, and then you can do the math stuff. A 10 kilogram mass hangs from a pulley straight down, and it's attached to a 1 kilogram mass on a 30-degree plane. Draw the free body diagram for each object separately. There is friction. And then draw it for the objects stuck together. This problem is actually in your all's recitation for this week. That one's 10 kg. That one's 1 kg. I'm just going to call it mass 1, mass 2. 2. 1. Try this. Can you draw the free body diagram for each object separately? So, step 1, part A, I got 2 objects, 1 and 2. Can you draw the free body diagram for each of those objects? Object 1 should have 4 arrows acting on it. Object 2 should have 2 arrows. And for object 1, you have to make a decision. Is this block going to go down the ramp or up the ramp? You have to actually decide that to draw the arrows correctly. Which block wins? All right, we'll do object 2 first because it's easy. Gravity points down. And then attention points up. Object 1, gravity pulls it down, string pulls it up. There is no normal force acting on object 2. There is no friction acting on object 2. Object 1, and this one I'm actually going to draw on the picture because I think it makes it easier to understand. So, gravity points down. Great. We're going to call that FG1. Tension force points in the direction of that. The normal force points away from the surface. Friction. You have to decide which way this block is moving. And which block wins is the question. Does the 10 kilogram mass block win or the 1 kilogram mass block win? It's going to be the one you hope. Yeah.
Well, I think it would be the 10
kilogram wins. Whichever one has more mass, gravity is going to affect more. Now, granted, if it's on a slope and it has more mass, you'd actually have to find the components and things like that. So, this is going to go downwards. To that end, if it gets pulled to the right, friction will go the opposite direction. Friction is always opposite the motion. Friction is always opposite the motion. All right. Now, if we then did this problem and we set up F equals ma and all that jazz, well, we're going to have to do this anyway at some point. Remember, you're going to have to break this into its components. You will have to split FG1 into its X and Y components. No matter what you do, you're going to have to do that. FG1. So you're going to find, we'll call this FG1Y, and we'll call this FG1X. Any inclined plane, you got to do that, y'all. You got to break the gravity into the X and Y. Now, awesome. Free body diagram set up. Woohoo. But honestly, part B is the one that I recommend doing. Can you draw a free body diagram where they're stuck together? Because effectively they are stuck together. That string is taut. They are one system. This is where I told you all, this is a 1D problem. This is a 1D problem where the path, the one dimension is this path here shown in, let's go with green. Green, this is a 1D problem. They can only move along this path. They have no other options. So what we're going to do is we're going to say left and right is the directions it can actually go. And up and down will be the directions it's not going. Can you draw the free body diagram for them stuck together? If you can, it is so much easier to solve this problem. It is so much easier to solve this problem if you can realize that they're effectively stuck together and left and right is the direction that they're going to travel. So what pulls them to the quote-unquote right? What pulls them to the quote-unquote left? Yeah, so what pulls them to the right? FG2. We got to clarify which gravity. Because what pulls them to the left? FG1X. If we look at our picture, what pulls this thing to the left? So that goes here. This goes here. Where's that one? What else do we have? We have a friction. Force of friction acting on one. And technically, if you really wanted to, you could draw the tensions. But guess what? They cancel each other out. For every force, there's an equal and opposite. So we don't need to put tensions in this. This is why this is so useful. And then the only other things that you might want to include on this, you could draw the up and down, i.e. the direction it doesn't go. So we could still draw, you're actually going to need this, FN1. And we call this one FG1Y. Because the next step now is, okay, MAX equals sum of forces in X. MAY equals sum of forces in Y. In the Y direction, and that up and down, it's going to be 0. Remember, it's a 1D problem. This problem, it doesn't leave that path. This block on the inclined plane doesn't fly off the plane. It doesn't go into the plane. So, yeah, that's the key to solving this problem, y'all. It's the recitation one. I do have the full worked out thing posted. Please check it out. Yeah. Tension is pulling up, and so friction always opposes the direction it's going to go. So object 1 is going to get pulled up the slope, so friction's going to oppose it. All right, try this one. If y'all can do this one, that's awesome. This is a great problem. See you all on Thursday, hopefully with very minimal rain.
So do we have to bring Scantrons?
No. You do not need to bring a Scantron. No Scantron needed. You just need your note card, a pencil, a calculator, yourself, And an ID with your name on it.
You still have four cards.
I don't, but just cut a piece of paper to a 5x8 size, and that's fine.
Which size?
Just